So far, when we write the Leibniz notation for the derivative, which is dy over dx, we've talked about how that's the same thing as applying this operation of d over dx onto a function y, and that it means the derivative of y with respect to x. And we've considered dy over dx as one symbol or one term by itself. What we want to look at now is what those two parts mean individually. So what are dy and dx when we separate those, okay? So to do that, we're going to start with this generic curve, okay? So it's a differentiable function f, so the derivative exists, and we have a point on here, which is going to be point P. So I'm going to put point P somewhere here, okay? And P has an x coordinate of x sub 0, and it has a y coordinate of y sub 0, or f of x sub 0. Here, let's label it with f. We'll say f of x sub 0. We also have a tangent line at point P because the function's differentiable. Okay, so let's sketch this tangent line. Something like that. Okay, now let's say that there is a second point somewhere to the side of point P, something like point Q. So I'll call this point Q. All right, and just like we did in 2.1 from the book when we did the definition of the derivative using the limit, we're going to define this in terms of its distance from the first point. So I'm going to call this x sub 0 plus, now I'm not going to use h, I'm going to use the notation delta x for this, but it's still, delta is changed, so this still means the horizontal change in x, okay? So that distance between these 2 points horizontally is delta x, okay? Our goal with linear approximations or using differentials to approximate is that we are going to look at how we can estimate the height of point Q using the height at point P and the tangent line. Okay, so let's add a couple of things here. We know that the slope of the tangent line comes from the slope of a secant line. Okay, and we know that the slope of the secant line has to have 2 points. So it's kind of like these are our 2 points, but instead of point Q approaching point P, we're just going to say that it's something that's fairly close. Now, for the purposes of our figure, so that we can see what's going on, imagine that we've just really zoomed in on this area, but imagine that this is a pretty small distance, like maybe it's 1/10 or 1 over 50 or just, 0.001, something small, okay? So here is what we have. We've got some different terms, so I'm going to use that to label, okay, or some different notations, all right? So this is the height y sub 0. Both notations are accurate there, okay? And we know that vertical change is change in y, okay? And so the change in height between these 2 points, point P and point Q, is this distance right here. So I'm going to label it over on the right, actually. So this distance right here is delta y, okay? This is not a calculus concept. This is an algebra concept. Vertical change between 2 points, change in y, we can represent with delta y, okay? Now, let's say that maybe we know what the graph looks like, but we don't know the actual equation for that curve. Or maybe we do have an equation, but it's very complicated and we can't evaluate this point by hand, okay? Or maybe we just have some data points and so we can get a trend and know a rate of change over here, but for some reason we can't just take this number and plug it into the function. What we want to do is we want to figure out how we can use this tangent line to get a point, okay? It's going to be this point right here, and we're going to use this point to approximate point Q, okay? In other words, the height of this point right here that has the same x coordinate but is on the tangent line instead of the curve, the actual function, this point is going to be used to approximate this value. And this will work as long as these two are fairly close together. Now, when we talk about fairly close, what we're really saying is as long as this x coordinate is close enough to x sub 0, or in other words, as long as delta x is sufficiently small, then this point can be used to approximate point Q. Okay, now some other notation stuff here. This vertical distance right here is going to be notated as dy. dy means the differential of y. I'm going to write this down below, so you don't need to write that down yet. But dy is the differential of y, and it is the vertical change between these 2 points on the tangent line. Okay, so we've got delta y, which is the vertical change on the actual function between these 2 points, and we've got dy, which is the vertical change on the tangent line between these 2 points. Okay, and again, our idea is that dy can be used to approximate delta y. Okay, so dy is used to approximate delta y. Okay, and I believe this is written down below as well, so if you don't write that down yet, that's okay. All right, let's look at what's happening algebraically here. Okay, we have this expression, and this should look familiar because this is the definition of the derivative that we wrote at the beginning of 2.1 from the book. Okay, now the notation is a tiny bit different. Instead of using an h in place of the horizontal distance, this uses a delta x because we're talking about change in x. Also, instead of a c value, this is using x sub 0. Okay, but it's still the derivative of the function f at a specific point, and it's still the limit definition. Okay, now remember that we're not going to be dealing with this point as it approaches this point. We just have 2 points that are fairly close together. So what we can do is we can say if delta x is sufficiently small, and sufficiently is going to be defined in the problem, like it will let you know how close you need to be. Okay, so if delta x is sufficiently small, then we can take the limit expression off of here and just use this quotient, okay, this difference quotient, and then we have an approximation here. So in other words, we can write this with, let me write this without the limit because the denominator is no longer 0. So we have f of x sub 0 plus delta x minus f of x sub 0, okay, all over delta x, and that is now approximately equal to f prime of x sub 0. So no longer exactly equal, okay, because we don't have a limit and we have 2 distinct points instead of 1 point that's approaching the other. Okay, now I'm going to do a little bit of algebra. I'm going to multiply both sides by delta x. So I get f of x sub 0 plus delta x minus f of x sub 0 is approximately equal to f prime of x sub 0 times delta x. So let's look at what these pieces are on the graph, okay? This right here, f of x sub 0 plus delta x minus f of x sub 0, that's the height of point Q minus the height of point P. So this right here, this side of the equation is exactly equal to delta y, okay? It's the change in height between point Q and point P, okay? This is y2 minus y1. Now over on this side, okay, on this side we have the derivative at x sub 0 times delta x, okay? Well, here's the thing about delta x. Delta x, the horizontal change between these 2 points, is exactly the same on the curve and on the tangent line. All right, so if we're going to use dy to represent the vertical change on the tangent line, the horizontal change is going on the tangent line is going to be represented by dx. So delta x is exactly equal to dx. Okay, so delta x, horizontal change between point P and Q, is exactly equal to dx, or the differential of x, which is the horizontal change between point P and the point we're using to approximate the height of Q. Okay, so over here, I'm going to switch that out for a d, and I write this as f prime of x sub 0 times the differential of x. Okay, so now what we have is that delta y is approximately equal to f prime of x sub 0 times dx. So delta y is approximately equal to f prime of x sub 0 times dx, okay? And this is equal to dy. Okay, so we are using the differential of y, which is f prime of x sub 0, or the slope of the tangent at point P, times dx, the horizontal change. We are using that to approximate the actual change in the function. Okay, let's look at this another way before we kind of summarize all of these terms and such. Okay, we know that f prime of x, we'll just look at notation here, f prime of x is the same thing as dy over dx. What we're doing now is essentially breaking these apart, multiplying both sides by dx, and then we have that dy is equal to f prime of x times dx. Okay, so you see how we are able to break these apart. We haven't been splitting them before, but really they do represent something on their own. They represent that horizontal change or vertical change on the tangent line. Okay? All right, so let's summarize these terms and then do some examples, because I know this is kind of a lot of stuff together. So delta x is some arbitrary change in x. It's going to be given to you in the problem. Like it'll say, you know, you're approximating the change in the volume as the radius increases from 5 to 5.2. So then your horizontal change would be 0.2. Okay, but that will be given to you. Dx, the differential of x, is exactly the same as delta x. Now, it is representing the horizontal change on the tangent line, whereas delta x is the horizontal change on the function. But again, they are exactly the same thing. Okay, horizontally, the changes are exactly the same. So delta x and dx are interchangeable. Okay, now delta y, this is an algebra topic, not a calculus topic. Delta y is the actual change in y as x changes from x to x plus delta x, okay? Or in other words, this is the vertical change on the function, okay? dy, which is calculus, the differential of y, is defined by dy equals, and we have it up here, f prime of x times dx, and this is the vertical change on the tangent line. Okay, and our process here is that we are going to use the tangent line to approximate the curve. All right, so I'm going to stop here and do the examples in the next video.